In this video, we will do an applied example involving antiderivatives. So what we'll form is what's called a differential equation, which is an equation that involves a derivative that we'll have to solve. Okay, so the example says a rocket has acceleration 6t feet per second squared. At t equals 0, the rocket is on the ground at rest. What is the height, aka the position, as a function of time? So to get this started, I want to recall that when we talk about a particle moving, or an object like a rocket, its position, in this case that's the height, that's h of t. If we take the derivative of that, well, let's put this in green actually. If we take the derivative of position, we get velocity. We get velocity, which is v of t. And if we take the derivative of velocity, then we get acceleration. The acceleration, which is a of t. So on the flip side, if I have acceleration, I would need to take an antiderivative to get velocity, and I would need to take an antiderivative of velocity to get position. So in our problem, we are given acceleration, a of t, is 6t. If I don't write the units, so the function is 6t. So this problem tells me some information about what's happening at t equals 0. So maybe I'll use that in a bit. But ultimately it's asking me to get the height. What is the height as a function of time? Okay, so when it says what is the height as a function of time, that just means I want to find h of t. I need h to be a function of t. Okay, so I have acceleration. Let's get velocity first. Velocity is going to be antiderivative of acceleration. So I have 6t, I write dt, because that's the variable in this integral. So antiderivative of this, if I do reverse power rule, I will get 6 and then times t squared over 2. Because I add 1 to the power and I divide by 2. And I get a plus c, because this is a general antiderivative. So this is going to be 3t squared. So more and more now, I'm just going to start to do that antiderivative. So instead of doing 6 times and then doing reverse power rule, I will just sort of say what we get after we do the reverse power rule. Okay, so we got the velocity. Now let's get position. So our height function is going to be the integral, or the antiderivative, of velocity. 3t squared plus c, where c is this constant. Okay, so when I do this antiderivative, maybe this one I can do in my head. A function whose derivative is 3t squared, that's t cubed. The antiderivative of c, of a constant, is ct. And then when I do this antiderivative, I will get another constant, plus d. Okay, and I could check this if I wanted to. When I do the derivative of this whole thing, I will get 3t squared. From this, I'll get plus c. And the derivative of d is 0, so I am getting back this function I had before. Okay, so now I want to use the other given info to determine the constants, the c and the value of d. Okay, so in this problem, it told me what's going on, a couple of things that are going on at t equals 0. One thing it tells me is it's on the ground. So the rocket is on the ground. And if it's on the ground at that time, that means the height when t equals 0 is equal to just 0. The height is 0, it's on the ground. Okay, so if I plug 0 into my height function, we'll get 0 cubed plus c times 0 plus d equals 0. And that just simplifies to d equals 0. So I know the value of d, so that's nice. Okay, the other piece of info the problem tells me is that t equals 0, the rocket is at rest. So at rest means it has no velocity at that time, or the velocity is 0. So the velocity when time is 0 is 0. Okay, so if I use that same thing, now I'm going to plug into my velocity function. So we will get 3 times 0 squared plus c equals 0. And that just becomes c equals 0. So this is nice. In this problem, both of the constants were just 0. That won't always be the case. Okay, but thus, we can now form h of t like the problem wanted. H of t is t cubed plus, I get ct, which is 0t, plus d, which is also 0. Okay, so I simplify, and h of t is just t cubed, and I guess there are units in this problem. The units of position, of height, are in feet. So this is t cubed feet, and that's my height as a function of time. So we have now finished our last goal for this section. This was a simple example of a differential equation, an equation that involved a derivative that I had to do an antiderivative of. So in general, the antiderivative rules are less systematic than derivative rules. So it takes more practice to get proficient at recognizing when do we use what for antiderivative problems. So you want to be ready to do a lot of different types of practice problems to get comfortable with antiderivatives.